All right, I'm very happy to introduce our speaker today, Elizabeth Worcester from Brookhaven National Lab. And Elizabeth got her undergraduate degree from Georgia Tech and then went to U Chicago, where she worked on epsilon prime over epsilon, K-TEF experiment, and got her PhD in 2007. And since 2011, she has been at BNL, and she has been promoted to a staff scientist a few years ago. And she is a member, as you see, of DUNE experiment, but also ICARUS and SBND experiments. She's going to talk about those today. Those are all accelerator-based neutrino experiments with Fermilab beams. And she has been a physics coordinator for DUNE in the last 5 years or so. So she certainly has a lot to tell us. So please welcome Elizabeth.
Thank you for having me. I'm happy to have the chance to talk to you about neutrino oscillation. I'll start off with just a pretty brief introduction to neutrinos and neutrino oscillation to sort of orient anyone here, especially who's not a particle physicist. And then I think probably the bulk of the time we'll be talking about long baseline oscillation experiments with a focus on DUNE. And then this could be a whole separate talk, but instead it's just going to be sort of a bit at the end on sterile neutrinos and short baseline oscillation. So just zooming all the way out to the standard model of particle physics, there's all of our known elementary particles. The neutrinos are neutral leptons in 3 flavors, matching their charged partners. So there's a nu e, a nu mu, and a nu tau. Neutrinos interact extremely weakly. The cross-section varies with energy, and I'll show you a plot later. But it's order 10 to the minus 38 centimeters squared per nucleon at the energies that we're talking about. If you go to a slightly lower energy, say the energy of solar neutrinos, the thing that you always hear people say is the neutrino could pass through a light year of lead before interacting. So it's a very weakly interacting particle. They're detectable, of course, only via their interaction products, and we'll talk more about in a moment. We know that the neutrino masses are very small, but we know that they're not zero. And the existing limits on the sum of the neutrino masses are order a few hundred milli-electron volts, where the strongest limits, I think, still come from cosmology, although there are direct mass measurements that are starting to be competitive. So the very first evidence for neutrino oscillation came from this experiment in the 1960s that Ray Davis was running at the Homestake mine, which is the future home of DUNE. And basically, he saw many fewer solar neutrino interactions than were expected from the solar model. And of course, everybody just thought the model was wrong. But we now know that what was happening was neutrino oscillation. So I think most of us who are of a young enough age that this was known have done this as a homework problem. I did this in the first year of grad school when it was still not totally known that neutrinos was oscillating. It was still an open question. But basically, since neutrinos have mass, they're created in a weak interaction in a definite flavor state, but that is not the same as the mass state. So the flavor state can be written as some linear combination of the mass states. And so if you want to propagate that, you propagate it governed by the Schrodinger equation in the same way that you would with anything else. And so if you want the time-evolved flavor state, then you just have this same linear combination of the time-evolved mass states. And so then when you plug in for the time evolution of the mass state, you get this phase. And then if you want the oscillation probability, you just take an inner product of the, your current time and position with the 0, time and position. And so if you do that math for a 2-neutrino case, which is a sort of simplified case that you can actually do, in a page or two, you end up with this oscillation probability. So the probability to oscillate from one state to another state depends on theta, which is some mixing angle. And then the oscillation frequency depends on delta m squared, which is the mass difference between the two states, the baseline, which is just the distance it's traveled, and the energy. The full oscillation probability, if you work it all out for the 3-neutrino case in matter, is much more complicated. So this is almost too small to read. But what you'll see is that there are a number of different mixing angles in here. There's also these terms that go like A, which has G Fermi and the number of electrons in it. So this is the matter effect. And what this comes from is that the oscillation probability can be impacted by the fact that neutrinos can undergo coherent forward scattering on electrons. And so electron neutrinos can do this via both neutral current and charged current, whereas the The other flavors can't because there's not, muons in your matter. And then there's also this phase delta CP, which if it doesn't equal 0 or pi is evidence for CP violation. So that's something we'll be very interested in. So this is the parameterization that we talk about experimentally. This is the PMNX mixing matrix. So this is the mixing matrix from the previous page, and it's parameterized in terms of 3 mixing angles and this complex phase. So theta 23 is about 45 degrees. We don't know its so-called octant. This just means, is this exactly 45 degrees or slightly higher or slightly lower than 45 degrees? If it's exactly 45 degrees, that would be theoretically interesting because there's no particular reason why that should be the case. So it might indicate some new symmetry. Theta 13 is measured to be about 10 degrees. Theta 12 is measured to be about 35 degrees. And delta is largely unknown. We're starting to have some measurements of it. And if this is not 0 or pi, then that would indicate CP violation. So the other thing you need in the oscillation probabilities is the mass splittings. And so since there are 3 neutrino mass states, there are 3 splittings. We know that the 1-2 splitting is small, order 10 to the minus 5. And we know that the 2-3 splitting is larger. What we don't know is whether the small splitting is the lowest state, and that would be called normal ordering, or if it looks like this, where there's a larger splitting and then 2 slightly heavier states. So this is called the neutrino mass hierarchy or neutrino mass ordering problem, and this is one of the things that we want to measure in our experiments. So just very quickly, a simple few words about observing neutrino interactions. So we observe neutrinos only by their interactions, of course. They're these neutral particles that interact very rarely. And in our detectors, we're mostly looking at their interactions with a nucleus, and in fact, with a nucleon inside a nucleus. So here's the Feynman diagram for what I've drawn here. The muon neutrino comes in, and let's say it interacts with a neutron in the nucleus. And so what it's doing is, in fact, it's exchanging a W, say, with the D quark inside the nucleus, and so that turns into a U quark. And you also get, you have to conserve lepton flavor, and so you get a muon coming out. So you have this approximately undetectable particle coming in, it interacts with your nucleon, and you get a final state muon, and you get a final state proton, and these are observable in our detectors. So to go a little bit more into neutrino interactions, the processes and cross-sections vary with neutrino energy and span a vast range of energies. So there's sources of neutrinos running across this vast energy scale. Today we're mostly focused on the GeV scale neutrinos that are produced by accelerators. At these GeV scale energies, there's multiple neutrino nucleus interaction processes that contribute. This plot shows 3 of them. This is the contribution from quasi-elastic, resonance, and deep inelastic scattering interactions. Sort of what these processes look like are drawn out over here. But basically, these are increasing complexity of final states. And so as you go higher in energy, you get to these more complex final states. But at the energies we're talking about for these accelerator experiments, you get non-negligible amounts of contribution from all 3 of them. So that is a sort of complicating experimental factor. There's also something called Magellan exchange current, which doesn't even appear on this plot because this plot is a little bit older and we didn't realize how important it was until a few years ago. But this is basically the initial state of the nucleus. The neutrino, instead of interacting with a single nucleon, can interact effectively with a pair of nucleons that are coupled. So like I said, these are just some examples of what these kinds of processes may look like. The quasi-elastic state has just the muon and proton in the final state. Resonance, you get an excited nucleon, and so you end up, and that can indicate a pion, so you end up with some pions in your final state. And deep inelastic scattering, you eject you start interacting at the quark level, really, and you end up with a sort of spray of hadrons in your final state. There's similar processes for electron neutrinos, similar processes for antineutrinos. There's neutral current interactions. And the details of both the initial nuclear state and the final state, sort of matter in describing the interactions that we're going to be observing. And all of this is actually not very well modeled at all. So even though there's been quite a lot of effort on it, so that's going to be a source of systematic uncertainty in our measurements. All right, so that's the end of the sort of general introduction to neutrinos. So going on to long baseline oscillations, what can we discover? Why do we care about these experiments? So the long baseline oscillation measurements are sensitive to these four mixing parameters, theta 2,3 and theta 2,3, those are, two of the mixing angles, delta m squared 3,2, including the sign, so that tells us the mass ordering, and delta CP, which is the CP violating parameter. So CP violation is, of course, incredibly interesting in particle physics. I've worked on it in kaons as well, so I guess I've worked on CP violation my whole career, and I think many people have. It's sort of been a driving force for discovery in particle physics over the last, 60 years or so. So symmetry and symmetry violation has really been a major driver of discovery. And in particular, leptogenesis requires CP violation in the high energy Lagrangian, which includes the right-handed neutrinos. And this is something, in the lepton sector, we have not observed leptogenesis. So it's important to note that there's no model-independent connection between the kind of CP violation that we're hoping to observe in these experiments and what is required for leptogenesis. So it's not like, we're going to see the CP violation that allows leptogenesis to proceed. It's more of a proof of concept. There are models where you can connect it. There are models where this low energy CP violation is enough to explain leptogenesis, but there's not a simple model-independent connection. So you have to be a little bit careful there, or theorists get upset with you. So flavor structure is another important thing that we can understand. If we understand the details of the values of these parameters in the mixing matrix, we may be able to understand why is the structure of the neutrino mixing matrix so different from that of the quark mixing matrix. Is there a flavor symmetry that can produce this pattern of mixing? How is it broken? Is nu tau mixing symmetric? This is exactly the octant question I was mentioning earlier. If theta 2,3 is exactly 45, then this mixing is exactly symmetric, and that would indicate maybe a new symmetry. We can use this to discriminate among models. There's many flavor and BSM models that make explicit predictions for the oscillation parameters. So if we measure them precisely, we can start to tell the difference between models. And that's what's illustrated here. These are just the predictions for cosine delta coming out of a number of different flavor models. And so you can see that if you start to get good resolution on delta, you can really exclude some of these models or provide some encouragement for some of these models if they happen to predict you correctly. And then finally, you can look for BSM physics explicitly in neutrino oscillations. You can look for evidence of additional particles or additional interactions that the neutrinos are undergoing that alter the oscillation alter the oscillation probabilities in a way that cannot be explained by just our picture of three-flavor mixing. All right, so the basic principle of these experiments is that you make a beam that's mostly muon neutrinos. I'll talk a bit more about that in a moment. But you basically measure the survival probability of muon neutrinos and the appearance probability of nu-e neutrinos in a nu-mu-dominated beam. And so you can optimize your choice of baseline and energy for the desired measurement. So what's plotted here is the oscillation probability. Blue is the nu-mu survival probability, and red is the nu-e appearance probability as a function of energy for a baseline of 1,300 kilometers, which is DUNE's baseline. And so you can see that this spot here, a little above 2.5 GeV, is the first oscillation maximum. And so on this plot over here, which is now neutrino energy versus baseline, you can see that sitting about here. So if you go down in this band of the first oscillation maximum, you end up in a very different baseline and energy regime. And so if you know that your baseline is down here and you want to measure the first oscillation maximum, then you have to look at a much lower beam energy. If you want to go to longer baseline, you have to go to a higher beam energy. That's just how the L/E dependence of the oscillations work out. And as I mentioned before, the appearance probability depends on all four of these parameters as well as the matter effects. So these are the oscillation probabilities that you would see at DUNE for true normal ordering for neutrinos on the left, antineutrinos on the right. And here now we're varying the value of delta CP. So this sort of shows you how the sensitivity to delta comes in. So red is if delta equals 0, blue is if delta equals minus pi over 2, and green is if it equals plus pi over t. And so you can see that there's definitely a rate effect. The probability is raised or lowered depending on delta, and there's also a somewhat subtler, but there's a difference in shape between these oscillation probabilities. So if you measure out this spectrum, that also gives you additional information about the value of delta. The delta CP increases the probability increases the probability for appearance in neutrinos, and then decreases it in antineutrinos if it equals minus pi over 2, and then it's the other way for plus pi over 2. So it has this asymmetric effect. And then the matter effect, so here we're seeing normal ordering, and that enhances the appearance probability for neutrinos and reduces it for antineutrinos. And then if we go to inverted ordering, I'll just flip between these a second, but you see that it goes the other way. So if you're in inverted ordering, then it reduces the appearance probability for neutrinos and enhances it for antineutrinos. So you can see it flipping like that. And so what you can see from this is that both the matter effect and delta induce matter-antimatter asymmetries. So if you're measuring a matter-antimatter asymmetry, there's going to be some degeneracy between whether it was caused by delta having some value or whether it was caused by the matter effect. So this is plotted explicitly here. So here, this is the matter-antimatter asymmetry that you measure as a function of the true value of delta. And on the left is for a short baseline, where you have very little matter effect, and then on the right is for a longer baseline, where you have a large matter effect. And so if you look at this shorter baseline, and this is the baseline approximately of the T2K experiment in Japan, then you see that for normal ordering and inverted ordering, if you measure a particular value of the asymmetry, you don't know which ordering you're in. You know, you could either be at this value of delta in inverted ordering or this value of delta in normal ordering. If the matter effect becomes large enough, then this degeneracy is split. These curves move further apart at longer baseline. And so once you get past about 1,000 kilometers, then there's no overlap. If you measure a negative asymmetry, you know you're in inverted ordering. If you measure a positive asymmetry, you know you're in normal ordering. And then you just have to work out what your value of delta is. So it allows you to measure both simultaneously without the confusion. All right, so when we're designing long baseline experiments, the requirements are both massive far detectors and high power beams. And this is really just to accumulate the statistics you need to make the measurements because neutrinos interact so infrequently. And if your source drops off as 1 over r squared, as you go to longer and longer baseline, you're fighting that. You also need sophisticated near detectors that are well matched to the far detector design in order to constrain your systematics. I'll talk a little bit more about that as we go through. So you have choices. You can choose your baseline. And you can choose to say maximize statistics and minimize matter effects. So that would be choosing to go with a shorter baseline. Or if you go to a longer baseline, you can lift the degeneracy, like we just talked about, between the matter and the CP effects. But now you have a statistics problem, right? And whatever you choose for the baseline determines the energy oscillation maxima. If you go to longer baseline, then that requires that you go to higher energy. And then that means that you're coping with more complex final states in your experiment. You can choose your beam angle. Some experiments choose to place their far detector slightly off axis of the beam. The effect of this, just because of the way the beam is produced, is to produce a lower energy beam that's more peaked at a particular energy. If you go on axis, then you have a broadband beam that is sort of a wider spectrum of energies. And then all of this will sort of inform your choice of far detector technology. Whatever you choose for your far detector technology impacts how much detector mass you can afford. You know, if you choose a very fancy detailed detector, you can only build so much of it. But then it also affects your ability to reconstruct complex final states. If you really need to understand all the details of these complex final states, maybe you do need a more detailed detector design. So all of that plays in. So currently, most of the parameters I've talked about are measured to about 3%, give or take, some slightly better, some slightly worse. We have these 3 major open questions in 3 flavor mixing. What is the mass ordering? Is the octant exact symmetry, or is it slightly higher or slightly lower? And is CP violated in neutrino oscillation? And so all of these can be measured by long baseline experiments. And then another question is everything I've just said complete? Are there only 3 flavors? Is the PM&X matrix unitary? Is nothing else going on? And long baseline experiments can contribute to this, but then we'll also talk about this a bit more when we talk about short baseline experiments. So there's 2 currently operating long baseline experiments in the world, NOVA in the United States and T2K in Japan. So T2K runs from Tokay to Kamioka, and its far detector is the Super Kamiokande water shrink-off detector. And it has a baseline of 295 kilometers, which is, why I chose, obviously, that example in some of the sort of more pedagogical slides. And then NOVA runs from Fermilab to Ash River in Minnesota. Its far detector is a segmented scintillator detector, so it's a tracking detector where you can work out images of the particle trajectories, and its baseline is 810 kilometers. So it's a whole nother talk to go into all the details of these experiments, but I can just show you that this is the most recent results from NOVA and T2K. So plotted here is sine squared theta 23 versus delta, and then the T2K best fit point is here. The NOVA best fit point is here, and this is for normal ordering. There's a similar plot that I just don't have room to put on for inverted ordering, but normal ordering is mildly preferred by both of the fits. And so what you see here is that, the confidence levels overlap fine. Everything is sort of fine, but there is some mild tension between the best fit values. And in fact, you can make these values much closer together if you choose the inverted ordering, which is slightly less preferred. So the point is that we don't know what these parameters are yet. Their measurements are being made, but there's still a lot of mystery happening here. These two experiments are working together to produce a joint fit. This is complicated because you have to try to understand. I don't think they're going to try to do a full combination of all systematics, but they do have to understand at some level the correlation between their systematic uncertainties to make anything like an interesting joint fit. So that's in progress, and I think it's expected to have a first result sometime in the coming year. So that brings us to the future experiments, which is what I mostly want to talk about. There's two of them, again, sort of mirroring the current experimental situation. There's T2HK, which is very similar to T2K, but with a much bigger FAR detector. So the idea here is to maximize statistics and minimize the matter effect to focus on rapid CP violation discovery. So they have a short baseline. They have a very large FAR detector, similar in design to the Super K FAR detector, except for now it's 187 kilotons, so it's just massive. And all the other parameters are similar to T2K, except for that the beam will be upgraded as well to 1.3 megawatts. DUNE is sort of a different, newer design that we're working on here in the US. And the idea with DUNE is to measure all the long baseline parameters, including the mass ordering, in a single data set, and to map the oscillation pattern as a function of energy for precision measurement. So we're not just trying to say is CP violated, we're trying to precisely measure all these parameters and observe whether or not the oscillation pattern matches what you would expect from three-flavor oscillation. So it's a new beamline. I'll talk about all these details. 1.2 megawatts. The FAR detector is a liquid argon time projection chamber, and the baseline is 1,300 kilometers. And it's on axis such that we're looking at a broadband spectrum of neutrino flux. This slide says almost all the things I just said, except for the part about the collaboration, so I'll just say that. It's a big collaboration, more than 1,000 collaborators from 37 countries plus CERN, so it's a massive international undertaking, sort of modeled on the LHC-style experiments. It's the first time we've done something this big in neutrinos. And the idea is that we'll use the Fermilab accelerator complex. This is existing accelerator complex that's currently being upgraded to get to the 1.2 megawatts. That will provide protons for the neutrino beamline, which is all new. The neutrino beamline will produce a beam of neutrinos that travel through the Earth to Sanford Underground Research Facility, where the FAR detector will be about a mile underground. So all of this is sort of based around the concept of liquid argon time projection chambers. So I'll just talk for a minute about these detectors. The idea behind these is to get detailed images of the final state particle trajectories. And this allows us to do clean separation of nu mu and nu e interactions, which is important if we're going to observe nu e appearance. Good energy reconstruction over a broad energy range, which is important because we are in this broadband beam. And a low threshold down to as low as a few MeV, which allows us to do low energy physics as well. So the basic way that these detectors work is that you have some large volume of liquid argon and you set up a drift field, which is about usually 500 volts per centimeter. So what happens is a neutrino comes in and it interacts and it produces some charged particles. As these charged particles travel through the liquid argon, they ionize the argon atoms, producing drift electrons. And so now, since the electrons are sitting in an electric field, they drift over to the anode. And then we have some sort of readout scheme on the anode. And in this case, it's wires. And so the wires are set up at angles to each other so that you can reconstruct, based on what wires are hit, you can reconstruct the 2D position of a particle in this plane. And then you get the third dimension from the drift time. So the drift time is the drift velocity is known based on the electric field, and so then you can work out that third drift dimension, which is why it's called a time projection chamber. And so then you get these, in different combinations of 2 dimensions, you get the particle trajectories, and then you can combine them into a 3-dimensional image. So here's an example of what an interaction looks like in a liquid argon TPC. This is DUNE Monte Carlo. So on the left is a nu mu interaction. The vertex is here. You see the long muon track. That's the sort of typical muon track that you see. Then this one has quite a bit of hadronic activity. So you see a couple different particles coming out from the vertex, including something here that showers. And here's a nu e interaction. So here you see the electron neutrino showering right at the vertex, as well as some other hadronic activity. So now, just to make this a little more real, this is real data that came from the DUNE prototype experiment, which ran in a charged particle test beam at CERN. So this is not a neutrino interaction now, but this is a 3 GeV charged pion that comes in and interacts. And here you can see the proton, and this place where it gets very red, the color scale is charge deposit. So this is the Bragg peak as that proton is stopping. And then there's a pi0 in the final state that decays immediately to 2 photons, and you can see there's this gap where the photons haven't pair produced yet, and then each one of them pair produces, and you get an electromagnetic shower here. So you can really work out all these like fun details of the interactions. So now I'm just going to step quickly through the pieces of the experiment. We have the beam, which is produced by LBNF. LBNF stands for the Long Baseline Neutrino Facility, which provides the beam, the underground facilities, and the infrastructure for DUNE. So you take 120 GeV protons from the Fermilab accelerator complex. This has been upgraded in PIP2 to 1.2, or is being upgraded in PIP2 to 1.2 megawatts, and will later be upgradable to 2.4 megawatts. The way you make a neutrino beam line is you have the protons from your accelerator complex impinge on a target, and you get a spray of charged particles, which you can then focus with magnetic focusing horns. You can sign select them, and then as they decay, they will decay to neutrinos or preferably or to antineutrinos, depending on which sign you've selected. And so everything else stops in matter, and your neutrinos just keep going pretty much forever. So we get this beam of neutrinos out, and then this is the flux that we expect to see from this neutrino beam line. So this is a log scale, neutrino energy in GeV. This is the nu mu flux. And then you can see a couple orders of magnitude down is the wrong sign background. So this is from unfocused particles where you got the antineutrino coming in the decay. And then you also have some small amount of intrinsic electron neutrinos, which will be a background to our newly apparent signal. And these come from, just other less common decays of the mesons in your charge beam. Next in line is the near detector. So we have a suite of near detector components that are designed to provide constraint on systematic uncertainty. Systematic uncertainties come from flux, neutrino interaction modeling, and detector effects. And the near detector can at some level constrain all of these. The heart of the near detector system is the liquid argon TPC. So this has the same nuclear target and detection technology, both far and near. So that has sort of a lot of strength to constrain what's happening at the far detector. It can't be identical to the far detector, and that's because it has to have some changes to the design to handle the higher rate environment at the near detector. There's just so much flux that the monolithic design of the far detector just wouldn't work. So we have this near detector that is a sort of segmented liquid argon TPC. This is a picture of the actual prototype, and this is real data taken in that prototype detector. This is just cosmic data, so you can see this is a downward going shower here. The near detector, the liquid argon TPC near detector, it's not really practical to make it big enough to contain muons of the energies we're interested in. So you have to have something called a muon catcher, which lives downstream of it and gives you information about when the muons range out. And so that's called the muon spectrometer, or TMS. And this sits just downstream of the liquid argon part. And in the second phase of DUNE, this will be upgraded to a much more sophisticated detector that will still serve as a muon catcher, but will also have improved capability for systematic constraints. There's a concept called prism, which is basically that we want to be able to move these near detectors off axis. So I talked about how you see different fluxes if you're at some off axis angle versus if you're on axis. And what we would like to do with the near detector is measure all of these. We don't want to have to pick an angle. We want to be greedy and have all the angles. And so we're going to do that. Liquid argon TPC and TMS can move up to 30 meters off axis to facilitate these measurements in different neutrino fluxes, which is important for systematic constraints. So if you're moving these guys off axis, you want to have something that stays on axis and monitors your beam all the time, and that will be the SAND detector, which is an on-axis magnetized low-density tracker and spectrometer, and this is reusing some components from the Colloquium experiment. And it has, all of these detectors, I'm talking about them in the context of the oscillation program. They also do their own sort of physics. They all have BSM physics, standard model physics, cross-section physics programs that, huge numbers of PhD theses and huge numbers of interesting physics results come out of. All right, so moving on to the FAR detector. It's a liquid argon time projection chamber, as I already talked about. So it will be located at the Sanford Underground Research Facility in Leeds, South Dakota. So this is something like a mile underground. This is the current home of LZ, the Majorana demonstrator. There's a whole physics lab. This is over here is where Gray Davis's original experiment was. All of this excavation for DUNE is new. There will be 4 caverns plus various support caverns and everything excavated at the 4850 level, making space for 4 modules of DUNE FAR detector, which is about 70 kilotons total detector mass. So this is just a picture underground, and this is a model of the FAR detector 1 module. There's 2 that are being built right now, and if you see this little tiny red square in the bottom, it has a person in it for scale. So these are very, very big things that we're building. It's real. It's under construction right now. Here's where the borehole broke through earlier this year in the caverns. And here is on site at Fermilab, one of the buildings for the new beam line under construction. So, assuming we build it and we take the data, this is what the data will look like. We'll be measuring spectra of neutrinos and antineutrinos, both in nu mu disappearance mode and nu e appearance mode. So these are the nu mu's, and you can see that these have this disappearance dip here. So you can see that they have this oscillatory behavior. So you can imagine fitting this and getting out all these oscillation parameters. And something like, well, the number of years is not completely clear, but something like 7 years, you'll get like 10,000 neutrino events, which is a really unprecedented rate of neutrinos. And then nu e appearance, the probabilities are lower, so these are smaller samples, but you'll still see something like order 1,000 events over a pretty clean background. The background here is dominated by intrinsic nu e's that just come along in the beam, and there's nothing you can do about those. And then the mis-ID backgrounds from neutral current and other neutrino types are really quite small. So you can really see quite a clean sample of nu mu's and nu e's, and you fit these together to extract your oscillation parameters. So when you do that, these are the measurements at DUNE that I'm personally most excited about. These are the sort of long-term high-precision measurements. So what's plotted on the left demonstrates sort of the ultimate reach of DUNE to measure the parameter delta. It's for 3 different exposures, but if you just focus on the green exposure, this is the resolution on delta in degrees as a function of the true value of delta for some very large sort of ultimate DUNE exposure. You can see it's like somewhere between 7 and 17 degrees, depending on the true value. The same sort of thing is plotted on the right. Now we've included sine squared 2 theta 1 3. So this is one of the other mixing angles versus delta. And what's interesting here is that the yellow shows the current best measurements. So theta 1 3, I haven't talked about this. It's been extremely precisely measured at reactor experiments, to the point that it's not expected that any experiment will ever really rival the reactor experiments in anything that's anticipated. But DUNE, in its ultimate precision, can come really quite close. And it's measuring theta 1 3, this parameter, in a completely different way, in a completely different oscillation channel than what was measured at the reactors. So if we get the same answer, then that is some evidence for unitarity of the PM&S matrix. If we get a different answer, then that's very interesting. So in addition to dramatically improving the precision on delta, we're also making this measurement of theta 1 3, whereas all the other experiments and the current experiments have to use this external constraint on theta 1 3. This is something that we'll be able to measure ourselves within DUNE. So these are the sensitivities to some of these discovery metrics that people are interested in. So on the left is the sensitivity. So this can be interpreted as approximately sigma. There's some, statistical analysis details so that it's not exactly sigma, but this is approximately number of sigma as a function of the true value of delta for 2 different exposures in DUNE. The width of the band shows 1 sigma variations of statistics, systematic parameters, and oscillation parameters. So this is not just the Asimov data set. Everything is thrown. So the sort of worst case scenario is the bottom point here. So even for the most unfavorable parameters and even for the most unlucky oscillations or fluctuations of statistics and everything, we're well above 5 sigma in some first phase of DUNE running. The plot on the right is a similar thing, except for now we're looking at the sensitivity to determine that delta CP is not equal to 0 or pi. You notice it goes to approximately 0 in the places where it is 0 or pi, because you can't prove that it's not something if it is that thing. And then it's easiest to prove that it's not 0 or pi in the places where it's furthest away from those numbers. So that's why it has this shape. We call it the McDonald's plot. But you can see that for large bits of delta CP parameter space, where, for very large bits of delta CP parameter space, we're above 3 sigma, and for significant fractions of it, we're above 5 sigma with these exposures. So again, there's a lot of discovery potential here. So in all of these plots, if you've been paying attention, you'll notice that I didn't put actual useful numbers on the plots. I put, in terms of exposures, I put these kiloton megawatt years, which has to do with how much far detector mass we have, how much beam power we have, and all of that has to do with the staging of the experiment. So the experiment is going to be built in 2 stages, or phases. And in phase 1, we'll have 2 of the possible 4 far detector modules at the far site. So we'll have something like 20 kilotons fiducial mass. We'll have the 1.2 proton megawatt beam, and we'll have the muon spectrometer that I talked about, but not this upgraded near detector that is better at constraining systematics. So what's plotted on the left here now is the sensitivity as a function of actual years for different phasing assumptions, and for different true values of parameter assumptions. So this left is all phase 1, and the light blue is if delta equals minus pi over 2, which is one of the places where it's the easiest to make this measurement. So if we get lucky and we are in this most favorable parameter space, it'll take less than 1 year of real years, real time, from when we turn on to make a 5 sigma determination of the mass ordering. It's like that dramatic if you're in that part of parameter space. Even if we're in sort of the worst case scenario, it takes less than 5 years to determine the neutrino mass ordering at 5 sigma. So this experiment is unambiguous in mass ordering. We will know without any question what the mass ordering is within 5 years of turning on, even without any upgrades. To do the exciting physics that we really want to do and that the experiment was designed to do, we need phase 2, which is to finish the far detector site, so fill out the remaining 2 modules, so that we'll have 4 far detector modules total, at least 40 kilotons of far detector mass. Upgrade the proton beam to 2.4 megawatts, and upgrade the near detector to better constrain systematics. And so what you can see in this plot on the right is the sensitivity for CP violation for 50% of delta CP values. So this shows you not just the best, most favorable parameters, but you're covering a significant chunk of parameter space. And the red is with the upgrade in place, and the green is just if you keep doing phase 1 forever. And you can see that if you keep doing phase 1 forever, you'll eventually get to 3 sigma, but it's just not really doing the experiment that you wanted to do with the precision that you wanted to do it. I should also mention that when we show these kinds of CP violation sensitivity plots, you can think of them almost as a proxy for the entire precision measurement program. If you can't do this, you can't do any of the other precision measurements that I was showing you. So if you realize this aggressive upgrade scenario, you do all the upgrades you need to do 6 years after the initial turn on, then you can get to 3 sigma CP violation sensitivity in 7 years, and you can get to 5 sigma sensitivity after about 11 years. So, this takes a long time, and it's largely because of the statistical precision that you need to make these measurements. A few words about systematic uncertainties. So you need something like order a few percent uncertainty for precision measurements. You have uncertainties from the flux, you have uncertainties from the interaction model, which, as I mentioned, is not really well describing world data at the moment, and you have uncertainty from detector effects. The sensitivity predictions, all that I just showed you, include detailed analysis of the impact from individual sources of uncertainty. So this part of the interaction model, this part of the flux uncertainty, this horn was moved by this number of centimeters, that kind of thing. It's all in there. So it's a fairly complicated analysis of systematics that goes into those sensitivity predictions. It's also important to understand that the impact of biases due to shortcomings in the interaction model is large. So I'm not sure I want to talk through every detail of this plot, but the basic idea is that if your model perfectly described the data and you just didn't know what the parameters of that model were, then that would introduce a certain amount of uncertainty, and that's represented by this dashed line. But if your model is just completely not describing the data, if it doesn't matter what parameters you put in, you're never going to perfectly describe the data because the shape of your model is just wrong in some way. That can introduce biases in your measurement that are not covered by these analyses, and then it just completely kills your sensitivity. So that's what's represented by these bands here. So you have to not only vary some unknown parameter by some amount, you have to take into account the possibility that your model never described your data in the first place. And you have to come up with ways to make sure that you would know that, so that you don't just measure the wrong thing and happily report the wrong number. And so a lot of effort, which I don't have time to talk about the details of, but a lot of effort has gone into that kind of analysis in preparing for DUNE, and that's part of the reason that we have the sophisticated suite of near detectors and the prism movement system, is to allow us those handles to make sure we're not making this mistake. And so, the near detectors are really a critical part of this program. All right. We also can do a lot of physics beyond the standard model in various ways. You can look for deviations from three-flavor oscillations, so things like sterile neutrinos, non-standard interactions, non-unitarity, Lorentz or CPT violation. And in any case like this, the measurements at DUNE and Hyper-K will be extremely complementary and help you disentangle whether or not you're seeing something like this or whether you're seeing some three-flavor oscillation parameter, because having the different baselines gives you these different handles. What's plotted here is just an example of a sterile neutrino sensitivity search from DUNE. There's many such plots in a sort of phenomenological style paper that DUNE put out that shows you all the BSM you can do. There's also a bunch of non-neutrino new physics signatures you can look at. One famous one is baryon number violation, like proton decay. Hyper-K or Kamiokande originally was a proton decay experiment, right? And we can still look for those kinds of things. Dark matter signatures, things like that. We can also do low energy physics, looking at supernova burst neutrinos. If a supernova burst goes off in our galaxy during the lifetime of the experiment, we'll see something like thousands of neutrinos, where people saw, I think, 20 from supernova 1987A, and there were thousands of papers written about those 20 neutrinos. So that'll be a really exciting data set for the astrophysics community. Again, there's complementarity among the experiments. DUNE will see mostly electron neutrinos because our cross-section is dominated by charge current absorption, whereas Hyper-K will be more sensitive to the antineutrinos because their cross-section is dominated by inverse beta decay. Information about both supernova physics, the details of the explosion and all of that, and about particle physics are embedded in the neutrino signal. And so you want to measure all this stuff, the time profile, the flavor composition, the energy spectrum. Here's an example in a particular model of a neutrino burst of the events that we'll see at DUNE as a function of time with different assumptions about the mass ordering. So for example, you get this very noticeable neutronization burst in the inverted ordering, and you don't see it in the normal ordering. It's possible to do supernova pointing with neutrino electron elastic scatters because the electrons from that tend to be very forward. So here's an example showing the pointing capability. Here's the true neutrino direction, and then this is some probability from an analysis. You can see that we can, at some level point to our neutrinos from supernova bursts, and that helps with melting messenger astronomy. So we can tell the optical folks where to look before the light gets here. Similarly, solar neutrinos are really interesting, especially because there's historically been a little bit of tension between the mixing parameters measured in reactor neutrinos and solar neutrinos. So this is a phenomenological paper from a few years back that showed if the reactor and solar neutrino central values stayed the same as they were then, and the errors were shrunk to what is believed to be possible, you could have this very strong tension. The central values have actually since moved slightly closer together, but the point is the kind of thing you want to measure and measure as precisely as possible. And DUNE should be able to do that. This shows a preliminary study from DUNE showing access to the AGP and boron-8 solar flux. This is hard because of things like detector resolution, thresholds, radiological backgrounds. DUNE was not designed explicitly as a super low energy experiment, and so there's a bunch of backgrounds that start to enter at the energies that we're talking about for solar neutrinos. But there's still a lot you can do, and in fact, people didn't even think we could do solar neutrinos originally, and now it looks like we can do them quite well, so that's exciting. All right, so now this is the summary of the DUNE part of the talk, but we have to keep going after this. So DUNE represents a major experimental advance for long baseline oscillation experiments, thousands of events, 5-level sensitivity to CP violation, precision measurements of oscillation parameters, including delta, and significant sensitivity to physics beyond the standard model. Systematics are a critical part of this. And these kinds of experiments enable a broad physics program: supernova, neutrino physics, baryon number non-conservation, BSM, solar. I haven't talked about this a lot, but there are opportunities to expand the physics reach with new detector ideas in phase 2. When we build those far detector modules in phase 2, we don't know exactly what they're going to look like, and there's a number of exciting ideas to possibly go after even lower energy physics, even things like direct dark matter detection, neutrinoless double beta decay, things like that people are talking about. So, one has to figure out how to make such a detector work, and one has to figure out how to pay for it, but there are a bunch of interesting R&D ideas to make DUNE an even more exciting experiment in phase 2. And then finally, DUNE and Hyper-K both will exist, and their design strategies complement each other. The things that we're trying to measure, there's a lot of overlap, but there's also a lot of differences. And those differences will help disentangle any observed BSM effects from three-flavor oscillation. All right, so normally I would be ready for a drink, but y'all asked me to give like a whole other talk on this other topic, so I'm going to try to do that real quick. So why are we interested in short baseline after I've just finished telling you all about long baseline? The reason is that based on the already measured oscillation parameters, we don't expect to see muon neutrino oscillation at small values of L over E. So this is the same stall plot I was showing in the beginning. This is oscillation probability. Blue is muon survival. Orange is NUE appearance, this time multiplied by 5. This is the baseline of the long baseline experiments that we've been just talking about, and there's all kinds of action there. They were designed to be put where there's action. If you look over here at the kilometer or so in the short baseline experiments, nothing should be going on. The survival probability should be 1. The appearance probability should be 0. There should just be nothing to see. And that means if you see anything here, you're seeing new physics. And so the reason why we are excited about this is that several experiments have seen things that might be oscillations at those baselines. So the MicroBooNE experiment is in the booster neutrino beamline at Fermilab, and they have seen an excess of electron neutrino-like events. So this is their data in the points with the error bars as a function of neutrino energy. And then the solid histogram is what you would expect from a standard model background. So there's a very clear excess here, and it's consistent with NUE appearance at L over E of about 1. Another experiment earlier than MicroBooNE called LSND saw something not exactly the same, but similar. So the significance of the excess observed by LSND is 3.8 sigma, MicroBooNE 4.8 sigma. The combined significance is 6.1 sigma. So there's something going on here that we don't understand. The possible explanation for this is sterile neutrinos. So instead of the 3-neutrino model we've been talking about, you can add an extra 1 or more neutrinos. And these additional neutrinos are so-called sterile, which means that they do mix with the standard neutrinos, so we can see these oscillations, but they don't have weak charge, which means that you don't have to say like LEP was wrong or astrophysics is wrong. You still have 3 neutrinos that couple to the weak charge. The 3+1 model is the simplest scenario. It's the one that we quote all the time. You see all the limits in terms of this. It's been almost completely excluded by disappearance data, so it's almost certainly not the full explanation, but it's still the parameters that we talk about when we're talking about this kind of oscillation. And basically, the whole way that this works is, remember, we had the mass splittings, the small one and the bigger one. So this is now an even bigger one, and it's order 1 eV squared. And so that allows it to appear at this baseline of L over E of about 1. All right, so if you combine the entire world data on sterile neutrinos, that was done in this review. So there's a bunch of NUI appearance data. And if you include the possible signals, there's a preferred region here with a delta M squared of around 1 and a mixing angle sort of here. Nu-mu disappearance sees no evidence of sterile, so these are all limits. If you combine the two, first of all, there's very significant tension between the two data sets. We don't really understand how we can get this data for NUI appearance and this data for nu-mu disappearance with the sterile explanation. But there is some region of parameter space that is sort of favored if you insist on combining them. So that's where we're looking. So we're doing that with the short baseline neutrino program. This is 3 liquid argon time projection chamber detectors and the booster neutrino beam at Fermilab. SBND is the near detector. It's 110 meters from the target of the beamline. MicroBooNE is at 470 meters. And then ICARUS is also at longer baseline, 600 meters, and is much larger. So MicroBooNE's been taking data, or has finished taking data now. They were taking data for the past 7 years. ICARUS just started taking data earlier this year, and SBND is in the process of installation and expects to start taking physics data in 2024. So we're about just over a year out. One of the big reasons why liquid argon TPCs are particularly interesting for this measurement is that they provide the capability to distinguish electrons from photons. And I already talked about this a little bit, but basically you can look for the gap between the shower start and the vertex for photons. So if here's your photon, there's some distance that the gamma travels before the first pair production. And so you might be able to just see this gap if you have a tracking detector that shows these tracks. And the other thing you can do is look for DEDX at the shower start. So if it's an electron, then at the very beginning of the shower, the DEDX is going to be about 1 MIP. And if it's a photon, then the first part of the shower is made up of an electron-positron pair, and so you get 2 MIPs. So you can use that as a handle. So MicroBooNE has done this analysis looking for some NUI-like excess at this baseline. The first results from their investigation were released last year. There were a ton of headlines about this. I'm sure all of you who have worked on searches appreciate the fail to find headline. That one's always fun. They released a suite of papers using different analysis techniques focused on 4 different final states, all of them looking for the NUI-like signal. And they were testing a very specific thing, which is, can NUI appearance fully explain the mini-BOONE result? And what they observed is that their signal is consistent with the three-neutrino model and disfavors the hypothesis that the mini-BOONE excess can be fully explained by anomalous NUI appearance. You have to be very careful and pedantic about the way you say this because they did a hypothesis testing statistical analysis explicitly to answer that question, not to answer the sterile neutrino question. So there was a lot of sort of overselling of that probably in some of these popular science headlines. There's a link here to an article that I was asked to write. I just put it there because it has convenient links to all the other articles rather than putting in 4 links. And it also has a link to a theory paper that I also talk about in this little Viewpoint article that is basically just saying, don't overinterpret this. These results disfavor one particular hypothesis, but they don't rule out all of parameter space. So then last month, MicroBooNE came out with another result. Oh, I'm sorry, I wanted to show you one more thing. So this is the actual data. So this is the 4 different final states. This is what you would have expected if mini-BOONE was from NUI appearance. And then this is what you would have expected if it was not, if there was no low energy excess. And so you can see that everything is consistent with the no LEE hypothesis. This one is a little high, but it's not very sensitive. It's a very low purity analysis, and it's within 2 sigma consistent. All right, so now, last month, new result from mini-BOONE, explicitly placing limits on the 3+1 sterile model. And this is the limits. I don't know if you will, we'll go to the next page in a minute. But the point is that this does not rule out a huge chunk of the parameter space. These are the LSND preferred regions. And so you're able to rule out at 95% confidence level some of this region, but there's still a big chunk of parameter space that is not ruled out by the MicroBooNE results. It's also interesting to note that you need to simultaneously analyze NUI appearance and mu disappearance because they can interfere if you're going to make the correct limits. All right, so the SBN program, as I said, multiple detectors at different baselines, same detector technology. So for some choice of oscillation parameters, here's the NUI appearance probability of each of the detectors. So SBND would see very little appearance, MicroBooNE and ICARUS would see nearly maximal appearance. You can combine these to contain your systematics. And you get this kind of sensitivity projection. So this is, again, delta M squared versus sine squared theta mu E space. So the red here is the SBN 3 sigma, and then dashed is 5 sigma exclusion contours. And the orange is the global fit preferred region, and the blue is the LSND preferred region. So you can see that we're really ruling out a much more significant chunk of this parameter space. It's hard to get everything, but we're, in principle, going to rule out or be sensitive to seeing oscillations in this large swath of interesting space. So just very quickly, the status, this is a picture inside the ICARUS hull. It's boring because the concrete overburden is on, and that means we're taking data, so that's good. We've been commissioning since 2021, taking physics data since June of this year. Here's actual data. This is a nu-mu interaction, so you see the long muon and the short, probably proton. This is the inside of the SBND detector that just finished getting built and is being installed as we speak. The completed detector will move to the SBND hull in something like a couple weeks. So significant non-standard model excesses have been observed in multiple experiments. There's also significant tension among experimental results. So we don't know what's going on, but it's something. There's a mystery. No evidence for anomalous oscillation and mu disappearance so far. MicroBooNE observes excess in NUI-like sample. LSND observes an excess in NUI-like sample. These are consistent with an EV scale neutrino. MicroBooNE disfavors the hypothesis that the mini-BOONE excess can be fully explained by NUI appearance. Set a first liquid argon TPC-based limits on 3+1 sterile neutrino model, but cannot yet fully rule out the sterile explanation. And then ICARUS and SBND will combine to more fully explore the parameter space favored by the global fits. And of course, as I sort of alluded to, it doesn't have to be steriles. There's other non-sterile BSM explanations that theorists are coming up with and that will be explored in these experiments. And future long baseline experiments also have significant sensitivity to anomalous oscillations, like I showed you in the DUNE plot. So now I'm really done. Liquid argon TPC technology is enabling unprecedented precision in neutrino physics, and there are important precision measurements and significant potential for new discoveries in both the short and baseline programs. Thank you for your attention.
Thank you very much, Elizabeth, for covering so much ground. Excellent talk. We have time for questions.
I wanted to ask you whether you could say something about how the DUNE and the T2K or T2K2 or whatever it's called.
Hyper-K, yes.
Okay.
Or you do
T2
mean the
HP.
T2K upgrade?
T2 Hyper-K. Okay.
Yes.
How they compare in their sensitivity and also in the time scale that we would see the results.
Okay. So I did not pack the plots, but I can talk about it for sure. So let's see, where's a good one to talk about? Let's go to this one. All right, so timescale first. DUNE is expected to have, first physics data late this decade. Probably the beam will be ready 2030-ish, plus or minus, I don't know, a year or two. Hyper-K is expected to turn on a little bit earlier. They have been saying 2027 for a while now. I don't have additional inside information like I do on DUNE as to whether that's completely accurate or not. But if everybody sticks to their currently advertised timelines, Hyper-K will come on a little bit earlier than DUNE. And all of the talk at the beginning about the different design choices, that's sort of what I'm talking about. Hyper-K, everything about Hyper-K is designed to get to CP violation sensitivity very fast. So they have no matter effect. So they'll take the mass ordering from somewhere else or from over a long period of time from their atmospheric neutrino sample, which is a hard analysis. But if they know the mass ordering, and if they come on before DUNE does, then they will probably get significance to CP violation sooner, because that's what they're built to do, is to do this rate measurement really fast. DUNE is designed with sort of two principles, one of which is measuring everything in the same data set. We don't have to take the external constraint from theta-1,3. We don't have to take the any external constraint on mass ordering. We'll do the mass ordering unambiguously, fit everything all in one data set. That feels cleaner. So, people want to phrase it as like, who gets to 5 sigma on this plot sooner? And I think if everything goes down exactly as expected, which doesn't always happen, but if it does, probably they'll get there sooner, if I'm being honest. But I don't think that matters super much. I think what's interesting and important about this experiment is the precision measurements. It's the ability to map out these oscillation spectra and see if they actually, look like this or they look like something else, if there's something else going on in this data. DUNE can do this and understand the details of the systematics in the final state in a much more precise way because of the liquid argon TPC. So it is, there's always competition, but I think the complementarities are more interesting, and the long-term precision of DUNE is the reason I'm excited about the experiment.
Sorry, this may be slightly inside baseball, but I understand there are some concerns over the signal stability in the argon over long periods. The signals are decreasing over time. I was wondering if you could, in the test configurations that have been run.
I don't think I'm familiar with what you're talking about. What experiments?
In your argon tests that you've been doing, signal sensitivity over a year or two, that you've been seeing decreases in the signal in the scintillation, the ionization signals over extended periods of time.
Yeah, I'm sorry. I just haven't heard that. I don't know which experiment you're thinking about. Proto-DUNE ran for a year and was reasonably stable. MicroBooNE ran for 7 years. I don't remember hearing anything. I mean, the purity can vary, right, depending on your filtration, and because you have to keep the argon pure, or the electrons as they're drifting will attach to the impurities and you lose signal that way. So if you have some sort of problem with the filtration system, or if the filters get old, you can have a change that then you have to replace the filters, and then it gets clean again and you're fine. I'm not familiar with any sort of actual degradation, though. I don't know, maybe you can point me to what you saw. I should know if there is one.
Thanks.
Other questions?
So I have a simple-minded question about backgrounds. I'm not at all a neutrino physicist.
Okay.
But, so you showed that there's some sensitivity to the directionality for galactic supernovae. Mm-hmm. Do you have equivalent sensitivity to solar neutrino direction to know that they're actually coming from the sun, other things like that? And in particular, what is your directional sensitivity to the actual beam coming from Fermilab? Like, what fraction of the neutrinos are going to be tagged as coming from that direction?
Okay, well, so there's a bunch of different questions in there that have to do with the different interactions that you're observing. So the supernova burst pointing sensitivity that I showed you comes not from the primary interaction mode or the most dominant interaction mode, but from the neutrino electron elastic scattering. And so you get that because the electron is very forward, and so now you know the direction. So for solar neutrinos, I think we could probably do the same thing and say that those ones are coming from the sun, but the bulk of the signal is not from that interaction. It's from the charge current absorption one. at those energies. So I think there's like two different things going on there. For the beam neutrinos, you know the beam gate, and so you use that much more than directionality to say that it's coming. The leptons do tend to be on the forward side, so you can use the angles. Like if you're at a surface detector, like the SBN program, and you have a bunch of cosmic background you're trying to differentiate from, then yeah, you can use the angles. The downward going ones are mostly cosmics, and the sort of straight going ones are coming from the beam. You can do that because the leptons are largely forward. But for DUNE, we're deep underground. It's very, very clean at the GeV energies. There's just not much else there. So the only backgrounds are beam-induced backgrounds. They're the intrinsic nuis, they're neutral current interactions, things like that.
Other questions? Let me ask you a couple. So I couldn't help noticing that MicroBooNE is about the same size as your short-based neutrino detector for ICARUS. So why not just move MicroBooNE and save some time and money?
Why not move MicroBooNE? All right, well, there's probably a couple things about that. So ICARUS is a lot bigger, for one thing, so we can accumulate statistics at the far
No, I'm talking about SBND.
Why
Why not use
not move-
MicroBooNE as SBND?
Yeah, so I mean, there's a couple things that I could answer. I mean, one is just historically the way the program developed. Originally, it was a slightly different program, and SBND was already a large part of the way to being built before this program came into existence. So I think a lot of it is historical. But SBND is also a much more modern version of the liquid argon TPC. Like a sort of side effect bonus of this program that I didn't talk about is development of liquid argon TPC technology at Fermilab, developing all the expertise, both to build these detectors and then to do all the reconstruction and analysis with these detectors. And so, for example, the cold electronics in MicroBooNE, the digitizing part of it was not cold, so and now all the readout electronics in SBND is cold, so you have better noise performance. MicroBooNE had some earlier versions of the readout electronics that had some issues when they were first installed, so they have a number of dead channels. They just have things about the detector that, because it was the first one, are not as good as what this newer one will be. SBND also has a unique capability in that a lot of effort has been put into the light collection system. I didn't talk about this hardly at all, but at the same time as you get the ionization electrons, you get scintillation light. You have a light collection system. You can measure that. You can do stuff calorimetrically with that side of the information as well. And so SBND has invested a lot in having a really high quality light detection system. So it's sort of just a next generation detector. So it'll just do a better job.
Right, and what is the main reason of not running MicroBooNE simultaneously with SBND and ICARUS? I mean, it costs you almost nothing, right? Just shifts.
It does not cost almost nothing because of the argon and the purification, and the cost of operations are actually not negligible. And the statistics at ICARUS sort of swamp MicroBooNE. I mean, you could have made that choice, but I think just financially it was decided that once these guys came on,
So
it
you
didn't
need
make
to
sense.
constantly purify argon? It's not sealed?
Yeah, there's a filtration system, and you have to keep it pure.
Okay, thanks. And my other question, you mentioned about the dark matter possibility in DUNE, dark matter detection. So what kind of threshold are you hoping to achieve for that?
Well, I mean, so these are all very hypothetical at this point, and people are doing R&D on different detectors. I think, and the problems are that there's an isotope of argon that is is decaying all the time, making a mess. And so if you really want to go below 5 MeV or so, you have to get rid of that background somehow. You can do it if you produce the argon underground so that you don't get this isotope. That's hard and expensive. I think you can get down to sort of EV-ish background. But I don't know the details of those.
But detectors like DarkSide, I mean, they work with what, 20 kilo electron volt threshold wick, is it about right?
Sorry, you mean for nuclear recall?
Yeah.
It's quite high, actually. It's 80 kV.
Right, but it's much lower than few MeV, right?
Oh, yes.
Yeah.
So can you still be competitive? I mean, you have
So
much
I
bigger
think it's,
mass.
I mean, I don't know the details of those analyses. I think it's a different detection strategy, but in principle, there's different like flavors of dark matter that you can look for. Like even in regular DUNE, there's a bunch of BSM studies where you can look for effects of dark matter that's produced in the target, for example, at the near detector and things like that. But yeah, the direct detection business is very hard, and I don't know the threshold numbers that people are talking about. It's been thrown out there as like you could maybe go after it.
All right, thanks, Bob.
Given the length of time that you expect to be doing this series of experiments, and given the quality of the detection technique, I'm sure someone must have done this, but have you looked into how well you can do the lifetime of the proton?
Yes, there are a lot of studies of that. It turns out DUNE would be most sensitive to the P decay nu decay because that's more difficult to be done in something like hyper-K because it's below threshold. But in DUNE, you can actually see the K to mu to E decay chain. The problem is that atmospheric neutrinos create a significant background to that process. So we can do pretty well with that mode, but not as well as you might have hoped because of that background. People will certainly do all those decay modes in DUNE. It's hard to be competitive with hyper-K just because of the mass differences. I mean, hyper-K is just so very large. They have so very many protons in it. But yeah, DUNE will certainly do that, and there's been a number of studies. One of the places that we do well is anti-neutron oscillation and annihilation, where you see the, 2GeV thing. But yeah, people have done all those studies. There's a whole bunch of, there's one of the papers in DUNE that came out recently that shows those sensitivities.
This is just a comment. Again, given the quality of the technique that you're using, the detector technique, with respect to hyper-K, it seems to me you have a real advantage in terms of background. That
Yes.
is, you can really distinguish your background much more easily than they can.
Yeah, I think that's
So that's
absolutely
just a
right.
comment.
No, I think that's right. And that's, I mean, people were really excited about the P decay nu mode explicitly because of that, because you really can, like if you look at simulation of P decay nu proton decay in a liquid argon TPC, it's cool looking. I think you can probably do better than have been done in our studies so far, but there are problems with final state interactions and there are problems with atmospherics that make it murkier than it seems like it might be. But yeah, it's definitely something we'll do.
All right, I think now Elizabeth really deserves her drink, so let's thank her again.
Thank you.